So let us continue from what we were discussing yesterday. So this is where what we discussed, that how does a process look in the memory. So first we discussed the difference between the terms process and the program, and we understood that process is an active entity. That means it is something which is under execution, and therefore it must have a representation on the memory. And this is the kind of representation. So this process, this space allocated to a process has all these parts. It has the text, which is the code of the program that it is running, the data, which can again be divided into global variables in this data segment, and temporary variables, local variables, etc. in this stack segment. Now I think from your knowledge of C programming and compilers, you know how this stack is used. So say when there is a function call, something is pushed onto the stack. Right, then the local variables of that function would possibly be created in this stack, and so on. And this is why when one function returns, then the calling function can no longer access the local variables inside the function which is returned. Right, because all these local variables of the function are created in the stack. Also there is this area called heap, from where if you dynamically allocate memory, it will be given from here, the heap. Okay. Fine, so we discussed these things, right? So just one question. So as shown in this diagram, the heap grows upwards and the stack grows downwards, right? So as more and more data is, say you have a program which is creating more and more dynamically allocated memory, so the heap will go upwards. And suppose there are lots of function calls, etc. So the stack will go downwards. Maybe you have a recursion where many functions are being called, so the stack will go downwards. So can it happen that this heap and the stack collide? Can it happen? And if so, then what is done? So can the heap, so first question is if the heap, can the heap and stack collide? And second question is if yes, then what happens? Okay, three people have answered. First of all of you are telling that this can happen, that the stack and the heap collide. But then all four are saying segmentation fault occurs. Try to find out, I am not sure. Why should a segmentation fault occur? Your program has not done anything illegal. Segmentation fault usually occurs when your program tries to access some memory location which your program should not access. Here nothing like that has happened. You are doing perfectly legal operations in asking for more dynamically allocated memory, when you are doing function calls, etc. Right, so I am not sure a segmentation fault should occur here. Okay, take this as a homework, find it out. A fault of course occurs, but possibly it's not a segmentation fault. And possibly, let's see, I'll also check up. I would be surprised if your program is terminated because of this. Right? So basically it means that your program needs more memory. And that's not a illegal thing to ask for. So I'm not sure if a segmentation fault occurs here. So do check it out. Okay. Okay, let's move on. Let's not discuss this context here. But yeah, I leave it as a homework to figure out. So what happens if the stack and the heap pointers collide? Yeah, so what Akshat has said, I would imagine something like that. Ideally, the OS should copy the process to a bigger memory space, or should allocate some more memory to this process. But do figure out. Okay, let's not discuss this point here. I leave it as a home task to figure out what happens. Okay. So let's go ahead with the next topic, which is process states. Okay. So if you think of the lifetime of a process, which happens, okay, Demochoti, I'm not discussing that topic much further, but since you have asked, if the stack starts overwriting heap, then there will be a massacre, right? Because heap contains useful data. So if the stack starts overwriting the heap, then your program will definitely malfunction. Therefore, stack overwriting the heap should not be an acceptable option. Okay, but as I said, I am not discussing that topic any further. I leave it as a hot task to figure out what happens. Okay. Okay, so let's continue with our discussion of process states. If you consider the lifetime of a process, that means lifetime of a process means from the point when say a new process is created, say you do /error out. So a new process is created till the time when the execution of the process will be completely over. Okay? So this whole lifetime of a process. If you think of that, then in this lifetime, a process can be in different states. And there are defined set of states which we will study, and a process may be in one of these several states at a particular point of time. And processes change state based on certain events. So this is similar to an automata, which all of you are familiar with. So what are the states? So here are the states which usually a process goes through. So new is the process is just being created. Okay. So execution has not started yet, the process has just been created in memory. Ready is that the process is waiting to be assigned to the processor. Okay. So for new, just after the process is created, it usually goes to ready. So it is now ready for the processor. Running is actually the CPU is allocated to this process and instructions of this process are being executed. Right? Next is a waiting state where the process is waiting for some event to occur. And then finally terminated, which is the process has finished execution. Now of course we will understand these states in more detail and how the process goes from one state to another. But before that, let me just clarify something. So here we write, the process is waiting for some event to occur. So where does it wait? Typically there is a separate area called swap space, which is meant for swapping processes in and out between main memory and disk. Main memory is limited. I think we all know that main memory, nowadays main memory is quite large, still it is limited. Compared to the disk, it is much smaller. So suppose a program has, a particular process is not active right now for a certain amount of time. Maybe it is waiting for some event to occur. So unless that event happens, or unless that event is completed, this process will never be allocated to CPU. Right. So maybe this event will be completed after 5 minutes. Maybe, right? Maybe a large painting job is going on and it will take 5 minutes. So for these 5 minutes, this process will not be allocated to CPU. So it might be wasteful to still keep the process in the memory for all these 5 minutes. Right? 5 minutes is a long time if you think of a CPU. So since it is understood that this process is waiting for some event to occur, and there is no point in allocating the CPU to this process until that event has occurred. Right? So in such a situation, it may be wasteful to still keep the process in the memory. So then the OS may decide to swap out the process in an area called swap space. Usually it is a separate area in the disk. Right? So when a process is swapped out, we mean that it is temporarily removed from the memory and kept in the swap space. And then again, let's say suppose this event for which the process was waiting finally occurs. So now the process is ready again. Then it can be swapped in into the memory. Okay. So just remember about this concept called swap space. Now is the one thing that we study the process state diagram. So we described about different process states. So a process can be in different states. And we said that the process goes from one state to another if some event occurs. So what are those events? Let's see. So the new is the first state in which a process finds itself. So it has just been created. So we know how a process is created, as in there will be this text segment, this code segment, the text segment, data segment, heap, stack. So currently we have to create this kind of an entry in the memory. So at that point the process is in new state. Okay. Then it becomes ready. So once all these things have been done by the kernel, so now the process has a full-fledged entry in the memory and it is ready to start executing. Okay. So it's in the ready state. Next, assume that at some point it will be allocated the CPU. So two programs usually come into picture. Again, these are kernel routines, kernel programs. One is the scheduler. We will study this in further detail later in the course, but just for now, scheduler is that program which knows which all processes are ready for the processor at this point. And out of all those, it will select one process to be actually allocated the CPU. Okay, let me repeat. Scheduler is a kernel program which knows that which all processes are ready at this point of time. And out of all those ready processes, it will select one and actually allocate the CPU. So then this process, which is actually allocated the CPU, will go from ready state to running state. Right? How the scheduler decides which process to allocate, that we will study in detail. There is a complete chapter called CPU scheduling. So we will study that in detail in a couple of weeks. But for now, understand that the scheduler knows which all processes are ready. From that, it selects one process. And very minutely, this task, so scheduler just selects the process which is to run next. Actual allocation of the CPU to this process is done by the dispatcher. This is also another kernel routine which allocates the CPU to the process chosen by the scheduler. So basically, several processes may be ready at a particular point of time. The scheduler selects one of them, how we will discuss, and the dispatcher actually allocates the CPU to this chosen process. Then the process goes into the running state. Okay. And let's say that a process has got the CPU, it is running, and let's say it completes the execution. Then it goes to the terminated state. Right, when you write an exit call, exit 0, or when your main function returns, then it goes to the terminated state. Right? Any questions till now? Of course, the process state diagram is not over. We will discuss that. But any questions till now? Okay, if not, let me proceed. Yeah. So see, now think about it. In a computing system of early days, this used to be the process state diagram only. Because we discussed this, things like batch processing and all. So in those times, one process used to be selected, it used to be assigned the CPU, it was allowed to continue until it completed, and then it moved to terminated. So in an old batch processing kind of system, this would be the process diagram. When the process is possibly new, then it is ready to be allocated to the CPU. At some point, the long-term scheduler, let's say, selects it, the CPU is allocated to it, then it becomes running, and it is allowed to continue until it completes, after which it moves to terminate it. Right? So this would be the process type diagram in a normal batch processing system. But in a modern system, we know that we want to make the system much more efficient, and therefore we have added many complexities. Things like, now we have many processors ready. Now we have many processors in the memory, and possibly a large number of them wants to be allocated the CPU. And we have discussed that the CPU will move in a time sharing mode. That means, say there will be a time quantum, and it will give time quantum to process 1, next time quantum to process 2, next quantum time to process 3, and again some circle back, next time quantum to process 1, and so on. Right? So we have added all these complexities, and therefore, in the modern system, the process type diagram is much more complicated. Let's see how. First, there can be something called interrupt, which we have studied in detail. So suppose a process is running and then interrupt happens, interrupt occurs. This interrupt probably comes from an external entity, like some IO device or timer or something. If this happens, we know that the control goes to the kernel, as in the kernel now has to execute. That interrupt handler has to execute. That means the kernel has to execute. So this process, which was running at present, has to be deallocated from the CPU. That means it goes back to the ready state. Okay. So this is one kind of complexity. An interrupt can come, due to which the kernel now has to run. Therefore, this process which was running goes back from the running state to the ready state. Next, let's see. Suppose the process was running, okay, and this running process asked for some IO event, asked for some IO operation, or it decided to wait for an event, right? At that point, the process goes to the waiting state, and after the IO or event completion, it goes back to the ready state. Now let me ask, what is the difference actually between these two mechanisms? One is the interrupt comes, we said it goes back directly from running to ready state. Second is IO event wait, it goes to a waiting state, and after the completion of this, it goes back to the ready state. What is the actual difference between these two mechanisms? In both these mechanisms, the process is going back from the running to the ready state. In one case directly, in one case through this waiting state. So what is the difference between these two mechanisms? Or why is this difference? Why did the waiting state not come here? What is the difference between these two mechanisms? Yes, so Dhrubil says that in case of waiting for the IO has to be done before the process can run again, right? Pankaj says interrupt was external and now this is internal, this waiting for an IO. Yes, Akshat has also the same idea, but that is correct. So the difference is that in this case, this interrupt was not raised by this process itself. This was raised by some external entity. So the process did not want anything. It is still ready. Okay. The process does not need anything specific from the kernel, or it is not waiting for an event. some external event happened due to which the kernel forced it out, you might say. Right? The kernel forced it out. The process was completely ready, it was running, it did not have any requirements, but the kernel forced it out. And therefore it directly went to the ready state. But in this case, the process actually asked for some help from the kernel. So it wanted from IO or something. So unless this event completes, there is no point in allocating the CPU to this process. Therefore it is sent to the waiting state. Right? And only after that IO event completes is it returned to the ready state. So when by ready state, a process is in ready state only when it is completely ready to be executed. Right? So if a process is waiting for an IO, then it cannot be said to be ready. Right? So I hope this difference is clear. But okay, the process type diagram has not ended yet, it is even more complex. So let's proceed. Okay, Ishan has a question. What happens when a process is not responding? I did not understand the question. So Ishan, can you unmute yourself? What do you mean by not responding? Rather, it's not clear. In Windows, for example, does not make sense to me. So, talk in terms of the OS, as in, what do you mean it's not responding? Okay, typical hangs can occur due to many different reasons. It can be due to a snag in the program itself. Right, so, I mean, not responding, this can happen due to many reasons. And so if you see, this process type diagram does not have a state called not responding. So ideally it should not happen. Right, however, it can happen due to many things, some of which we will discuss a bit later in the course. So for example, you have opened so many processes that, say again, okay, you see this context switch takes some time. We discussed that. There is an override associated with context switching. So one process has the state of one process has to be saved, then another process has to be loaded, some registers have to be written back in memory. So these things take time, these things are an overhead. So maybe you have opened up so many processes that the CPU is constantly just switching between processes. It is not being able to do anything for any process. Right, maybe. I'm not saying this is the definitive reason for program not responding. But it can happen that you have opened up so many processes that most of the time is going on between switching processes and no useful work is being done for a particular process. So that can give an illusion of program not responding. So again, I would like to differentiate between this. A process not responding is usually not the case. But you might say that we have a window open and we are not seeing any activity in that window. So that can happen due to many reasons. It can happen due to a snag in the program itself, which you are running. Or it can happen because many programs are running and the CPU is just waiting, it's just engaged in switching from one process to another. It is not being able to do anything specific for a particular process. Or it might also happen that unknown to you, your process is waiting for some event. Right? Unknown to you, your process is waiting for some event which is not happening. So a process not responding, as you say, not responding to the user, can happen due to many different factors. So again, it is practically impossible to say that why is a process not responding. However, a process not responding to the kernel maybe is not a valid situation. Right? So let's say, the kernel has allocated a process, but it says no, I won't go, I'm not responding. That is ideally should not happen. So I believe Isha's question was meant for it is not responding to the user, or the user has the illusion that the process is not doing anything useful. That can happen due to many reasons. Okay, any other question? Okay, let me proceed. So as I said that, so we have discussed it here, right? So I hope the difference between this mechanism of going back to the ready state and this mechanism of going to the waiting state and then the ready state, hopefully the difference is clear. But as I said, the process state diagram is actually more complicated, and let's see the complications. One thing is this swap out. So as I said, there are lots of processes in the memory and memory is limited. So maybe new and new processes are all coming up, etc. So at a point is reached where not all processes can be accommodated in the memory. Right? So every process takes a lot of space in the memory. So if it happens that a lot of processes have been started by different users, not all of them can be accommodated in the memory. Then what happens, the kernel has to do is that some processes which are even ready, but still some processes have to be swapped out. That means remember the swap space which we discussed a few slides back, is usually a area of the disk which is meant specifically for this, that the memory is not sufficient to hold all processes, therefore it is swapped out. And then it is kept in the state of swapped out ready. Okay? So it is still ready, but it has been swapped out. Maybe due to some high priority processors being given that area, etc., etc. But then there is this provision of swapping out. Okay. Okay, I see there is another question. Abhijit says, can you give an example of interrupt which puts a process from running state to ready state? Okay, I can, but I would like you all to do it because we have discussed this. What can be an interrupt which puts a process from running state to ready state? It's simple, we discussed it in detail. Exactly what Sriyas says, timer interrupt. Right? So a process has completed running for the time quantum that it was supposed to run. So a timer will interrupt, and we discussed this mechanism in detail, that the kernel sets up the timer and a physical clock is decrementing the timer, and when the timer reaches zero, it's a counter kind of thing. So it's the physical clock is decrementing it. When the timer counter reaches zero, the timer interrupts. So this interrupt was not generated by the process itself. However, if this interrupt happens, then the kernel will run, because now possibly the next process has to be allocated, and this process which was running will be placed in the ready state. Okay. Fine. Okay. Let me proceed with the process state diagram. So yeah, so as I said, swapped out ready. This mechanism is there because it can happen that not all processes are being allocated, can be accommodated in the memory. So a process may have to be swapped out. Also, a process which is in the waiting state can also be swapped out. Right? Because again, the swapping out usually happens if there is not enough memory. Right, so both from this state as well as from the ready state as well as from the waiting state, a process may need to be swapped out. Okay. Also check that suppose a process was in the waiting state where it was swapped out. That means it was waiting for some IO, input-output operation, but it was swapped out. Now, while it was in the swapped out state, while it was in the swap space, the IO completed, right? The IO completed. So the IO device interrupted the OS, interrupted the kernel. Now the kernel sees that, oh, okay, this process was swapped out, but it is no longer waiting. The event that it was waiting for has been completed. So then the kernel can bring it to the swapped out ready state. Okay. Agreed? So again, a process can be swapped out both from the ready state and the waiting state. And there can be a change even in the change in the state of the process even while it is swapped out. So from swapped out waiting, it can go to swapped out ready. And finally, there is one other arrow which is missing here, one other transition which is missing in this process state diagram. Can you point out what it is? Exactly, Ayush, good. Ayush Akshat, good. Swap in. So we have discussed about swap out. What about swap in? So exactly, Zubir has given the answer. This is the transition which is left. From swapped out ready to ready. So this is the process of swapping. Maybe some amount of space has now been freed on the memory. So the OS decides that, and the kernel decides that, a process can be swapped in. So, or maybe it's the turn of this process to run now. So if it is in the swap space, it has to be brought in the memory. So this process is called swapping. I mean, this mechanism is called swapping. So from swapped out ready, it goes to a ready state. Okay, so this is the complete process state diagram of a modern CPU, a time sharing kind of CPU. So if you have any questions, tell me about this process state diagram. Okay, so that's a question. How does the kernel recognize which state a process is in? Yes, you have yourself given the answer, which is true. That there is not a bit, but yeah, there is an entry. We will study that. There is an entry in the memory block of a process itself, which says what state it is in. Right? There is of course an entry for every process that which state it is in, and this state is changed by the kernel. Okay, there is one small thing missing in this process state diagram. I mean, no transition is missing, that is, as far as I know, that all transitions are there. Maybe a small detail is missing in this process state diagram. Any idea? Maybe somewhere here. Yeah, Isha has pointed out the right thing. Good. So see, a process is in the running state. When can it go to the terminated state? One option is, of course, what is shown here, that the process has completed, so it calls exit or it calls like return 0 from main, something like that. But then some event can also force it to go from running state to terminated state. Things like exceptions. So, if I done a divide by 0 operation, or you trying to access some memory which it was not allocated. So then this process can be forced from the running state to the terminated state by the kernel through like a segmentation fault or something like that. So that is also there. It's not always, so what is shown in this picture is the voluntary mechanism like exit, and there is this forcible mechanism also where a kernel can actually force a process to go from running state to the terminated state. Okay, any other questions about this process state diagram? Okay, if not, let me proceed. And feel free to write here if you have questions. Okay, now the question is Srivas asked, how does the kernel recognize which state a process is in? That is now that, in fact, that will be answered now. So it's good that you asked this question just before. So for every process, there is something called a process control block that is maintained by the kernel. And as you will see, that says which state the process is in. So a process control block, in short a PCB. So each process is represented in the kernel as a PCB, also sometimes called the task control block. Contains many pieces of information associated with a specific process. Okay, let me clarify one thing, just a minute. We are not talking about this here. When we are talking about process control block, we are not talking about this picture. This is the representation of a process in the memory. Right, so text, data, stack. This is the representation of a process in the memory. But apart from that also, the kernel has our own kind of representation of the process, which is a process control block. That is much smaller than the picture that we saw earlier. But this is you might say this is a data structure internal to the kernel, which the kernel uses for controlling various processes. So it contains many pieces of information associated with a specific process. But this many pieces of information in the PCB does not include the code or the variables, etc. These are bookkeeping information which the kernel has to maintain for controlling different processes. Okay, I hope the distinction is clear. So what is there in the PCB? All these things. So first note what Srihash asked, process state. So the PCB has an entry which stores which state the process is in. Right, so the process cannot change its own state, only the kernel changes its own state. The kernel changes the state of a process. Okay. Also, every process has some ID, some number that is stored, process number. Right. Then the program counter, the location of the instruction to execute next. Then the registers. Remember we discussed this, that the state of a process is indicated by the value of the CPU registers. So that has to be kept here. That is there in the PCB. The CPU scheduling information. So priorities, scheduling, queue pointers, these things would become more clear as we go ahead. But all these things are used by the kernel for controlling different processes. Next, memory management information. You might have come across these terms in your COA course. Right, so which part of the memory is allocated to the process? Have you come across these terms in the COA course? Page table, base and limit registers. Have you come across these terms in the COA course? Okay, so you are studying page tables, yeah. So something like that, okay, fine. Okay, fine. But yeah, so these are for memory management. So which part of the memory is allocated to the process, etc. Then again, accounting information. So CPU used clock time elapsed since start, time limits, process ID, etc. Okay. Yeah. So, right. Then IO status information, IO devices, list of open files, etc. So suppose your program has some files open. So those kind of information are also stored in the PCB. So essentially the PCB does not contain the code or the data of the processes, but the PCB contains several information which are used by the kernel to do the bookkeeping or to control different processes. One of them is the process state. The other things are things. I hope you are connecting some dots. As in these things we discussed earlier. Like so every process is allocated an area in the memory. So someone must remember that which area in the memory is allocated to this process. So that is done by using this PCB. And see, one thing you have understood over these 3 years or 2.5 years which you have spent here. Whenever a program has to remember something, there has to be some data structure. There have to be some variables, some data structure. So even for the kernel, when you say that someone must remember that which area of the memory a process is allocated. So again, the kernel has to remember that, for which it needs data structures, it needs variables. Okay. So this PCB is that data structure which a kernel uses to remember all these things about different processes. So every process has a PCB and which is used by the kernel to remember about this process. Okay. And in fact, the kernel uses a structure like this called task struct, okay, where it has all these fields. Like if you actually go down to some representative kernel code, you might see something like this. So process ID, PID. Actually, there is an underscore here. It's not coming for some reason. PID underscore T is a data type. I mean, it's a user-defined. What is that called? Type def kind of thing. It's basically a unsigned integer. But yeah, PID underscore T is a type def version of that. So that is the process ID. Then see long state. Right, so state is this is the entry which will contain the state of the process. It's of type long. And then there are many different bookkeeping entries. Right, so basically this kernel uses this kind of a structure to store the PCB of a process. Okay. Fine. Okay, so we will just discuss context switch. Any questions before that? So process control block. So we studied 2 representations of a process. One is in the memory, as in the text segment, the code segment, the stack, and so on. One is the PCB, which the kernel uses. So PCB representation is internal to the kernel. Okay, Akshay says, why we need a long for state when we have 3 possibilities? Okay, this I cannot answer. This, true, that why should that require? I mean, maybe this was just thought of the designers thinking of the future. Maybe someday there will be so many states defined where. But really, I don't know. Right, so true, maybe but short 2 months should have been enough. So why is there a long, that I don't know. But yeah, I hope you realize the fact that there should be some entry which should tell the kernel which state a process is in, and the kernel should be able to change that state as and when events happen, etc., etc. Right. Okay, any other questions? Okay, let me proceed then. So now we have been speaking of this mechanism where one process was, so process A was executing, a timer interrupt came or something happened, process A was deallocated from the CPU and the CPU was allocated to another process, so B. So this mechanism is called a context switch. Let us understand that in a bit more detail. So just to explain this, let us consider a multi-programming of 4 programs. So P1, P2, P3, P4. Right, so it's just, so we are not actually demonstrating the mechanism here. We have in fact discussed the mechanism of context switch earlier, but this is just a conceptual model of 4 processes running in a multi-programming environment. And these processes are independent, as in they don't have a relationship to one another. Processes can have a relationship between one another. We will study that next week. But assume that for now these processes are independent. They do not have any relationship to each other. And the processes run sequentially. Now, the main thing to understand here is that, so yeah, we have these 4 processes, but the main thing to understand here is only one program is active at any instant, or only one process is active at any instant. Though that instant can be very short. So this is the point which I have been trying to make you understand since almost the beginning of this course. Remember that just to remember examples and so on, that only one program is active at any instant. So see, let's say there are these 4 processes, A, B, C, D. From the CPU's point of view, at one point of time it is executing A, maybe the next instant it is executing B, next instant it is executing C. Again next instant it has gone back to B, then next instant it has gone to D, and so on. So this is the CPU's point of view. At a particular instant of time it is just executing one process, but then the switch from one process to another is happening very rapidly. Right, so if you think of 1 second, maybe the CPU gives some time to every process within that 1 second time. And CPU can do this because it is very fast. So even if it gives maybe 10 milliseconds to a process, that process does something useful. Right? So this is the CPU's point of view. However, the process point of view is that every process thinks that I am executing sequentially, as in I am executing all the time. Right? So the process point of view is that there is no relationship between A, B, C, D. We are just executing. Every process thinks that we have a dedicated CPU and we are executing. And this abstraction, which is given by the OS, makes it easier for us to write programs also. We don't have to worry that, our program will be executed for a few minutes, then again it will be switched off, it will be swapped out, or it will be deallocated from the CPU. Again, sometime later it will be given the CPU. We don't have to worry about these things. So the process point of view is that it's simple, just 4 processes are running. But from the CPU's point of view, it's circulating among the processes. So maybe another representation can make this idea clear, which is called a Gantt chart. Gantt chart, have you come across this term? Maybe in some other course also, maybe software engineering or something like that. Gantt chart. Okay, if not even, so Gantt chart is a chart which on the x-axis is time and the y-axis shows which activity happens at what time. So this is the Gantt chart, so a sample Gantt chart of this scenario. At this point A is executing, at this point B, at this point C, then again B, then B. But see, at a particular point of time only one process is executing. But this is only known to the kernel of the CPU. The CPU can say, maybe the CPU can figure out that at different points of time, different processes are executing, and at one particular time, only one process is executing. Right. Okay. But from the perspective of the processes, every process thinks that I am executing sequentially. And so basically we have discussed this. What happens when the CPU switches to another process? First, the kernel saves the state of the old process and loads the saved state for the new process via a context switch. And we have discussed this mechanism in detail. Like how does a context switch happen? Usually an interrupt comes either from the timer or maybe this process itself has asked for an IO operation or something like that. Because say at a particular point of time, let me go back to the previous slide. Say at a particular point of time, process A is running. Suddenly kernel cannot come out. So we often see people making this mistake. But suppose A is running, we will ask them, so how does context switch happen? They say this process A is running. Then the scheduler comes and schedules process B. So the question is, if process A is running, how can the scheduler even run? The scheduler is also a process. It's a kernel process, but it's a process. So if A is running, the scheduler cannot run. So something must happen so that the control goes from A to the CPU, to the kernel. That means the kernel should start executing. And we have discussed this mechanism in detail. It usually happens via an interrupt, which can be the timer interrupt or something like that. So at that point, the kernel starts running. First, what it has to do is saving the state of the old process. And then it loads the saved state for the new process, which is to be run next. Right? And what do you mean by saving the context of a process? Now we know that PCB is the context. Right? So PCB is the context, which actually says what the different values of the registers are, what is the state of this process and so on. So this PCB has to be saved. And so you understand that more complex the operating system and the PCB, the longer it takes to switch. Right? So not all operating systems have the same structure of the PCB. So in this course, we are not discussing any particular operating system. But I would imagine that the PCB in Windows is very different from PCB in Linux or PCB in BSD. Right? So we are not discussing any specifics of any operating system here, but then understand that more complex you make the operating system and more complex you make the PCB, it will take longer to switch. Okay. So basically the process will look like, the picture will look like this, just another pictorial representation to make things clear. Suppose process, so we are now talking about only two processes, P1 and P2, and there is the kernel. So suppose at this point P1 is running, so P2 is idle, kernel is also idle, P1 is running. Now an interrupt comes, kernel wakes up, kernel starts running. It saves the state of process 1 in PCB1. Okay. Then it restores the states from PCB2. So it basically allocates the CPU to process 2. Then process 2 starts executing. So the CPU is allocated to P2 and P2 starts executing. During this time P1 has become idle. See. Right. So the moment the interrupt came, P1 became idle. The kernel ran for some time. It saved the state of PCB1. It restored the state from PCB2. And then PCB2 starts executing. Maybe at some later point of time another interrupt comes. This time to PCB2. This time while P2 is running, another interrupt comes. So then kernel will do the same thing. It will save the state of P2 in PCB2. It will restore the state of P1 from PCB1. And then again it will allocate the CPU to P1 and P1 will start running. Meanwhile P2 has become idle and so on. Right? So this is the context switch. So this picture is showing two context switches. Once from P1 to P2, next from P2 to P1. So whenever there is a context switch, at some time the kernel runs, it saves the state of the previously running process, it restores the state of the next process which is to be run next, and then the next process starts running. Okay. Right, so that is our discussion till now. We will continue discussing more about processors because there is a lot more to discuss about processors, which is a very important concept in MS. That we will do next week. So yeah, so I don't have anything else to say today. Do you have any questions? Okay, if not, then fine, thanks. Let's end this class. We will continue next week. Thank you.